Swayam Prabha. Digital India. Educated India.
So when you go back to the you have seen before, you will have the last equation, which is always the same. The torsion equation is this. And so, same thing as before, derivative of this once, and then replace this into here. You end up with this equation here. Actually, this equation is a little bit more complicated than the equation before. Because the previous one was a second order equation, Euler equation, and we knew the solution. How can we solve this? The same as before. Let's try to do this. So if I help me in checking, the equation is this. The fourth derivative of phi with respect to x4 minus gjt. The second derivative of phi with respect to square minus m square e. I used this Greek letter, capital gamma, which you have written there. What is that? It's times phi equal to 0. Okay. Yes, yes, yes. Okay. Now let us make this position here. 2 alpha no, there is something that I think here there is also, yes. And beta is equal to this. Okay, is that correct or not? 2 alpha equal to gjt divided djyy, is that? Divided by e gamma. Okay, no, there is some. Okay, no, it's e gamma, but no, yeah, correct that there is some. There is this. Okay, make this. This equation becomes, if I make that position, is just a changing of just changing some notation. Okay. So this is the second order equation that you have to deal with. Now, probably you know from your differential calculus or the partial differential equation, what is that? How do we solve this equation? We associate to this equation an algebraic one in which we put a parameter lambda, which is a number, and we raise it to the same power as the order of the derivative of the unknown function. So here we have the fourth derivative of phi. So we put lambda 4 minus 2 alpha lambda square, because we have the second derivative, minus beta. Phi is the unknown function. We consider it as the derivative of order 0. So lambda to 0 is equal to 1. Well, this is a more palatable equation because it's an algebraic equation, but still it's a fourth order one. But we also realize that is a particular fourth order equation because we only have the fourth order term and the second order term. So if I put lambda square equal to t, this equation becomes t square minus 2 alpha t minus beta equal to 0. Well, this is a second order equation that I can solve easily. So let me write it back. So the equation is lambda 4 minus 2 square minus beta 0, which becomes t square minus 2 of t minus. And the solution of this equation is t equal alpha plus or minus alpha square plus beta. But I realize one thing. T equal to alpha plus alpha square plus beta is a positive number because alpha and beta, they are just physical quantities. They are naturally positive. So alpha plus square root positive, it's a positive number. But alpha minus alpha square plus beta is a negative number. Well, you can say, okay, no problem. I have a second order equation and one root is positive, the second one is negative. Yes and no, because this t is lambda square. So when I have to extract lambda equal plus or minus, let's call it t1 2, the square root of t1 2, it's okay because I am extracting the square root of a positive number and it's not a problem. It will be plus or minus the square root of alpha plus the square root of alpha square plus beta. But if this is t3 4, when I have to extract the square root of a negative number, I have to transform this into -1 minus alpha plus alpha square plus beta. And so this is plus or minus e. This is the imaginary unit, the square root of -1. So actually I have lambda 1, lambda 2, lambda 3, and lambda 4. I can also write plus or minus gamma, plus or minus I delta. And then what does the theory of differential equation tells me? It tells me that the solution is something like A1 E lambda 1x plus A2 E lambda 2x plus A3 E lambda 3x plus A4 E lambda 4x. So that is my solution. And I have 4 boundary conditions. Actually, the solution can also be written in a slightly different form, which is what you find in the slides. So what has changed with respect to the second order equation that we have seen before? is that besides having the sinus and cosinus, we also have the hyperbolic sinus and hyperbolic cosinus. And how do we get from the x equal to a1 e lambda 1x plus blah, blah, blah to this? Well, simply the fact that sinus hyperbolic of gamma x is this. And the sinus is E sinus hyperbolic of gamma x is this one. Here we have the hyperbolic sinus of delta, and this is E delta x minus by 2. And the cosinus is E delta plus minus delta by 2. Once more, these formula are by Euler. He was the, handler, the big master of all this theory. And just remember, delta and gamma, we have written them here. We will go back to them when necessary. But now you see, okay, we have settled this, okay? Now what we have to do in order to complete our solution? Boundary conditions, because we have in that solution, in that function, A, B, C, D, which we don't know. So we need 4 boundary conditions. But from the experience that we have garnered before, we actually immediately can write only 2. It's phi equal to 0 in x equal to 0. And phi in x equal to n equal to 0. We need to find other 2 boundary conditions. We do only know that our beam at the edges is torsionally supported by a fork. We call it a fork. And the fork prevents the rotation, phi equal to 0, but leaves the warping free. If the warping is free, you do not have parasite effects. So the parasite effects are here. The parasite effects are here. If your warping is free, this moment is equal to 0. But in order this moment to be equal to 0, the only possibility that you have is that the second derivative of u is equal to 0, or that the second derivative of phi times h half is equal to 0. That is the only possibility that you have. So we write the other 2 boundary conditions as phi second x equal to 0 and phi second x equal to L equal to 0. Remember one thing, even if we see them as boundary conditions on the rotation and on the second derivative of the rotation, these are 2 different types of boundary conditions, because here phi equal to 0, you are assigning a boundary condition on a deformation, which is the rotation. Here, the condition you are assigning is the condition on a moment, on a static action, which you correlate to the second derivative. But remember that this is a kinematic boundary condition and this is a static boundary condition. There is also a wise way to, because actually you have here a system of 4 equations in 4 unknowns. which could not be so easy to be solved. Okay, so let's try to rewrite it and see how do we do. Phi x equal, let's rewrite it, a sinus of gamma. Gamma x plus b hyperbolic cosinus of gamma x plus c sinus delta x plus d. And let's start writing the first boundary condition. Phi in 0 is equal to 0. Well, I put x equal to 0. The hyperbolic sinus is 0. Hyperbolic cosinus in 0 is 1, so it's b. The sinus of 0 is 0, so this disappears. The cosinus of 0 is 1, so b plus d equal to 0. If I write now the second kinematic boundary condition, phi in L equal to 0, I find a hyperbolic sinus of gamma L plus b hyperbolic cosinus of gamma L plus c sinus of delta L plus d cosinus of delta. Okay, that's fine. Now the other two boundary conditions are on the second derivative. So first of all, I have to calculate the second derivative, which is a gamma square, the hyperbolic sinus, plus b gamma square, the hyperbolic cosinus, minus c delta square, the sinus, minus d delta square, the cosinus. Because the hyperbolic function, they keep repeating the derivative, but they do not change the sign. The trigonometric function, they keep changing between sinus and cosinus, but it's sinus, cosinus, minus cosinus, back to sinus. So you have a fourth periodicity on the derivatives. Well, let's do the second derivative of phi in 0 has to be equal to 0. So what do you have? This is 0. You cancel out. You have b gamma square, c delta square, the sinus of 0 is 0, minus d delta square equal to 0. And then we have the second derivative in L, which will be a gamma square hyperbolic sinus of gamma L plus b gamma square hyperbolic cosinus of gamma L minus c delta square sinus delta L minus d delta square cosinus delta. So what I do realize that it's true that this is a system of 4 equations in 4 unknowns, but I have two of them where only 2 unknowns appear. So let's solve that first and find b and d, and then we go for the others. So if I pick up the first equation here, what I can write? I can write b equal to minus d, or d equal to minus b. I pick up this and I bring this here. And what I find b gamma square plus delta square equal to 0. Now, b is a number. I don't know what number is that, but it has to be a number. Gamma square plus delta square is also a number, because remember, it's written on your slides that gamma is the square root of alpha plus the square root of alpha square plus beta, and delta is the square root of minus alpha plus the square root of alpha square plus beta. So if you replace this into here, you find that gamma square plus delta square is equal to twice the square root of alpha square plus beta. But alpha and beta are numbers which come from the stiffness characteristics of the beam. So they cannot be zero. If they are zero, it means that beam does not exist. So the only possibility that you have here is that B is equal to zero. But if B is equal to zero, also D is equal to zero. And it means that here you cancel this, you cancel this, you cancel this, and you cancel this. That's nice. Because in this way, we are still solving a system of 4 equations in 4 unknowns. But we are solving it, splitting it into 2 parts. If you have to solve a system of 4 equations in 4 unknowns, either you write your own Excel or Python or whatever, or you have to go with the determinants of the matrix and so on. It can be quite complicated. But now let's rephrase now the boundary conditions. Let's rephrase them, having eliminated B and D. So we have that A, the hyperbolic sinus of gamma L plus C, the sinus of delta L, has to be equal to 0. And A gamma square, the hyperbolic sinus of gamma L, minus C delta square, the sinus of delta L, has to be equal to 0. Now, this is a system of 2 equations in 2 unknowns, and our unknowns are A and C, the integration constants. As a matter of fact, this is a homogeneous system. So all the equations are equal to 0. Actually, we do know that this system surely has one solution, which is the so-called trivial solution. A equal to C equal to 0. But then you will be right to come to me and say bad word, because I say, okay, it's 11 pages of differential equations to end up with A equal to B equal to C equal to D equal to 0. Come on. Why this effort, this waste effort? Well, because we are looking not for the trivial solution. The trivial solution is A equal to C equal to 0. We are looking for a non-trivial solution. And we know from linear algebra that for this system to have a non-trivial solution, it's the determinant of its coefficient matrix has to be 0. So you have to calculate this determinant here. So the determinant is minus d delta square sinus of delta L hyperbolic sinus of gamma L minus gamma square sinus of delta L hyperbolic sinus of gamma L. This has to be equal to 0. Yeah. But let's make one step at a time so that we follow better. Well, then you also can write, change the signs and do this. This is a product of 3 numbers. One number is gamma square plus delta square. We have already seen before that this comes out into a number that is intrinsically positive and cannot be 0. Hyperbolic sinus of gamma L is 0 only when gamma L is 0. But once more, if gamma or L are 0, the beam does not exist. So the only possibility, as our friend was saying, is sinus of delta L equal to 0. And once again, it's not delta L equal to 0, but delta L equal to pi. So delta equal to pi. But what was delta? Delta is the square root of minus alpha plus the square root of alpha square plus beta equal to pi over L. So first of all, I raise to the square both members of the equation. And I find minus alpha plus the square root of alpha square plus beta is pi square over L square. Okay? Now, I see that I still have a square root in my equation. But before raising to the power, just bring this minus alpha here, because if we don't do this and raise immediately to the power, we're still keeping to have the square root. So we have the square root of alpha square plus beta equal to pi square L square plus alpha. So the square root of alpha square plus beta equal to pi to the 4 plus 2 alpha pi square over L square plus alpha square. Alpha square and alpha square I can simplify. And I find beta is equal to, let's write in this way. Agree with me? I simply, use it some. But what was beta there? Beta is equal to m square divided by the square root of e jyy e gamma. So if I equate this, I have this. So you see that there once more, then you have m square equal to something. We will rewrite now in a moment, and we will extract the no, sorry, there is not the square root here. Okay, it's like this. Okay, there is not square. The square root appears after one. So what is the result of this equation? It's once again m. It's once again a critical bending moment. And I can solve this. So I have, so it's m square divided by e jyy e gamma equal to pi 4 over L4, 1 plus 2 alpha L square over pi. And if I solve for m critical is equal to pi square L square. Well, E can stand E. The square root of jj gamma, the square root of 1 plus 2 alpha square, where 2 alpha, I remind it to you, is this one. But since gamma we have written before is this, if I bring this into here, this is pi square j square e jyy 1 plus 2 alpha. Then let's try to look into this formula here. So you remember let's do like this. You remember the Euler theory of the column like this. The value of the critical load. Pi square E j over L square. We have here pi square E j over L square. You see that there is some coherence. Well, this is a force. This is a moment, and you have another length to match it up. Look at the term under the square root. Look at the term under the square root. What does these terms here? There is a term GJT E gamma L square. 2 alpha L square is this, divided by pi. So it's 1 plus something. You have to interpret it as a corrective term. When it's 1 plus something, it means that it's a corrective term. What does it depend on? Well, at the denominator, you have the Desenvenant torsional stiffness. And at the denominator, you have the Vlasov stiffness. If the Vlasov stiffness is much bigger than the Desenvenant, that ratio becomes smaller. So 1 plus something small, and the square root of 1 plus something small is close to 1. So that corrective term does not count that much. So we can say that, and then we close it more or less, then M critical is equal to pi square over L square E JYY H over 2. Imagine this cross section here. And this is the bending moment, and you say this is M critical. But this M critical you can see as an N critical times H. Is this the way in which we have said that this I cross section work? So N critical, if you work it out, is pi square E L square EJJ over 2, which we have seen before is more or less the moment of inertia of the flange. So actually, your critical moment is just corresponds to the critical axial load of the compressed flange. The tensile flange has no problem of buckling because tensile force does not lead to buckling. What does this mean? This means that if you are in the famous resort and have no calculator and so on, but just want to have an idea, just look at the flange and try to consider it as a, a thin slab in its own plane, which can buckle in this way. This helps you, there are 2 very nice books that I recommend you to read by Salvadori, Why Structure Stands Up and Why Structures Fall Down. In the first one, Salvadori states one thing, that the structural engineer, the engineer, must feel the structure. If you don't feel the structure, you are just doing, it's like, when I tell my wife, I am not preparing a meal, I'm cooking, because it's something different. If you are preparing a meal, you are just not thinking. If you are cooking, you are selecting the ingredients, you are thinking of whom are you cooking for, it's different. So you can do your calculations, or you can design structures. 2 different things. Do your calculation, it's something that does not belong to you. Okay, in the end, you have a result. Designing a structure, it's something that you feel as your own. If some of you is doing his own or her own PhD, if you don't feel the project as your own, okay, you just muddle around. You must feel things as your own, and you must be proud of that. It's like when you cook, you make a nice meal, and you say, oh, yeah. Then you make a photo, you share with friends. And so that is, and we must feel the structure. So realizing this connect, this is, okay, you can see this as simply a mathematical results. Okay, you have played with the numbers, we have played with the symbols. Okay, this is equal to that. Okay, that's very nice. But if you realize, say, oh, really, that is a buckling problem due to a moment, but I have decomposed it into the couple of forces. That means that the nature, the physics of the problem is speaking to me with a language, and this language are these equations. Mathematics is a language that we learn how to speak and how to handle. It's not something other than us. Okay, then I will finish a little earlier because I realized that it has been. But there is another thing that we addressed beforehand. Nowadays, now we have ended up with M critical equal to something. And I don't remember who of you came to me before asking me, but so you were. Well, how do I make my safety check? Well, I have my acting bending moment, which must be, well, not equal to, less than M critical, with some safety factor also. But then what is this acting bending moment? Because when we have started with the slides this morning, we had a problem which was this. But hardly in the reality you have a beam with a constant uniform bending moment. Most likely, if that beam is the beam that we have seen in the picture, we have something like this, and our bending moment will be a parabola with this maximum equal to PL squared over 8. So which number shall I put into here? Well, one can go straight forward and say, okay, I want to sleep quietly all through my life. Pick up PL squared by 8, which is the maximum bending moment, and guarantee that it's lower than the critical moment. Perfect. You are over designing, or you will say, no, I am over giving safety. Okay, two different points of view. But over designing, you know, maybe not always wise. And it's not because of cost, because over designing means more material. We must be. Over designing may not be wise exactly in the respect of what we have seen this morning in the lecture of Professor, when he spoke about capacity design. And I also told you yesterday, when you design the foundations, you have a column which goes into that foundation that we have seen yesterday and we have seen also this morning. You design the foundation not because of the forces and moments which are there, but you design the foundation based on the resistant moment of the column. So if you have over-designed your column, you are forced to over-design even more your foundation. So this is in earthquake design, over-design is not always a wise choice, because you can say over-design means better safety. Okay, yeah, means higher stiffness. Okay, but it's not always a wise choice. Also because remember this, especially in earthquake, if you over-design, it means that you make a stronger element, but it also means that you make a stiffer one. Earthquake, as we have learned this morning, is not a force. Earthquake is a non-uniform motion of the ground. If the motion is non-uniform, it means that you have an acceleration. This acceleration of the ground is transferred to the structure, and the structure has its own vibration characteristics, so it can modify this acceleration. And it ends up that the masses of the structure, they vibrate with an acceleration. So that mass with that acceleration is the inertia effect that we consider as the force equivalent to the earthquake. But the stiffer is the structure, the worse is the case, because the stiffer is the structure, it means that you pick up the acceleration of the ground and you do not modify it. Precast structures work reasonably well, and then you have to design the connections properly, in seismic regions because they have the stiffness which is appropriate for them. And they can, dampen, in a sense, the effect of the ground motion. Their dynamic characteristics are such that they reduce the peak ground acceleration, and so they work more effectively. Over-designing it may counteract these characteristics. So over-designing is not always the wise choice. So going back to this, it means that we cannot simply say PL squared by 8 less than M critical. So what do? We have to calculate an equivalent bending moment. Equivalent. But what is the equivalence criterion that we can have? The moment? But torsional moment is something which appears when it deforms. You don't have torsional moment. You have just bending moment. So one way could simply be, I pick up a bending moment, equivalent bending moment, so that the area of this blue rectangle is equal to the area under the parabola. So in this case, my equivalent bending moment is 2/3 of PL squared by 8. This could be a criterion. Another way of doing things is I have my structure here. This is P. This is the bending moment here. And I also know that this structure here deforms in this way, and I have a maximum deflection. Well, let's call V because we have called it delta in another way. V is equal to 5 over 384 P L to the 4th divided by EJ. What I am looking is a structure which is loaded in this way with M equivalent, which has a deflection V here, which is equal to this. Can you calculate the deflection for this beam? ML square, yeah. Square, L square by 8 EJ. Because what do you do with? You apply a load, and this load is equal to the equivalent divided by EJ. And the displacement by the Morse analogy. So the maximum bending EJ L square by 8. So you have M equivalent L square by 8 EJ equal to 5 over 384 P L to the 4 by EJ. So this is 8 and 384. This is 48. Yes. L square, and this becomes L square, EJ and EJ. And you have M equivalent is equal to 5 over 48 PL square. What was before was PL square by 12. With the other technique was PL square by 12. So you see that in this case is slightly higher, because if it would be 4 over 48, will be exactly 1 over by 12. So the two approaches are more or less equivalent. There is really a 8% difference into that. But yeah, also in this case, it's good to, have the feeling of the numbers. Okay, well, I think I have spoken